Let's determine the maximum voltage that can be obtained from a Van de Graaff generator. My motivation for creating this video was a comment to my video in which I described a rotary electrostatic motor. I was driving that rotary electrostatic motor with a Van de Graaff generator, which is described in this video. And the comment was in regard to the DC voltage I was claiming my Van de Graaff generator was producing. So let's look at the theoretical maximum voltage that can be obtained from a Van de Graaff generator. Analyzing the maximum voltage I can obtain with the Van de Graaff generator utilizing a Coke can would be rather difficult. So instead, I'm going to analyze a Van de Graaff generator where a metal sphere is used instead of the Coke can, which is a more typical shape for a Van de Graaff generator. Here's our generator with a charge of plus Q on it. And let the radius of the sphere be designated as R sub sphere, and let the origin be at the center of the sphere. From the symmetry, the form of the electric flux density field is going to be a function of R and only in the radial direction. And this will be for a radius greater than the radius of the sphere, and when the radius is less than the radius of the sphere, the electric flux density field will be 0. So now we can apply Gauss's law to determine the exact form of the electric flux density field. And Gauss's law is that the integral of d dot ds around a closed surface is equal to the charge enclosed. So we will choose a sphere of radius r as our Gaussian surface. So the integral of d dot ds around that sphere will be d times 4 pi r squared, where 4 pi r squared is the surface area of that sphere, and that's equal to the charge enclosed, the charge Q, on our Van de Graaff generator. So our electric flux density field D is equal to Q over 4 pi r squared in the radial direction. Assuming the sphere is surrounded by air, we know the electric flux density field is equal to the permittivity of air, which is very close to the permittivity of free space, epsilon sub 0, times the electric field intensity. So from this expression, we can solve for the electric field intensity. Therefore, the electric field intensity is Q over 4 pi epsilon sub 0 r squared when r is greater than the radius of the sphere, and it's equal to 0 when r is less than the radius of the sphere. As charge builds up on the sphere, the electric field intensity is going to increase, and the maximum electric field intensity is going to occur on the surface of the sphere. So the charge on the sphere is going to increase until the electric field intensity on the surface of the sphere reaches the dielectric breakdown strength of air. The dielectric breakdown strength of air is 3 times 10 to the 6 volts per meter. So the maximum charge on the sphere is 4 pi epsilon sub 0, the radius of the sphere squared, times 3 times 10 to the 6 volts per meter. And this came directly from this equation where we put the breakdown field strength in for the electric field intensity, r sub sphere for the radius and solving for q, which would now be q max. The potential on the surface of the sphere minus the potential at infinity is the amount of work it takes to move 1 coulomb of charge from infinity to the surface of the sphere. So putting our form of our electric field intensity in for our sphere and integrating, we find that this potential difference is equal to the charge on the sphere over 4 pi epsilon sub 0 times the radius of the sphere. So selecting as a reference that the potential at infinity is 0, the voltage on the surface of the sphere is equal to Q over 4 pi epsilon sub 0 times the radius of the sphere. So now if we put in the maximum charge that we can obtain on the sphere before breakdown occurs, we can compute the maximum voltage we can obtain on our Van de Graaff generator. So Vmax is equal to Qmax over 4 pi epsilon sub 0 times the radius of the sphere. So let's substitute in the expression we obtained for the maximum charge on our sphere, which was 4 pi epsilon sub 0, the radius of the sphere squared, times our dielectric breakdown strength of air, 3 times 10 to the 6 volts per meter, and that's all over 4 pi epsilon sub 0 radius of the sphere. So the 4 pi epsilon sub 0's cancel. One of these radiuses in the numerator cancels with the one in the denominator, and so we get for the maximum voltage that we can obtain the radius of the sphere times the dielectric breakdown strength of air, 3 times 10 to the 6 volts per meter. So for a sphere with the radius of 5 centimeters, which is 0.05 meters, we see that the maximum voltage that could be obtained would be 150,000 volts. This sphere is actually 10 centimeters in diameter. So a sphere of 5 centimeters in diameter would be approximately the same size as the Coke can, but the Coke can, of course, will not get anywhere near 150,000 volts before dielectric breakdown because of the high curvature along the edges of the Coke can. But the voltage on the Coke can should easily get up to 10,000 volts.